In this video, we will discuss how to write ionic equations and then net ionic equations for different reactions. When I teach aqueous compounds based on solubility rules, I feel like a lot of the time I will repeat the phrase that if it's aqueous, it is really just ions. And that's because ionic compounds break apart into their ions because they're going to be soluble in water most of the time. And this is a phenomenon where these compounds are commonly called electrolytes. And so if I have a solution of sodium chloride, they're not really stuck together like we may write it in NaCl. It's really sodium is kind of doing its own thing and chloride is doing its own thing. And then if we evaporate away the water, we will force those two to come together and make NaCl solid. But if there's water around, they'll split apart and go on their way. And so we're going to go through some practice problems to show exactly how one might go through about making a net ionic equation. So the first thing here is we're going to need to use solubility rules, and we're going to just go ahead and make the regular molecular equation like normal. So if we have calcium chloride, calcium is Ca2+, chloride is Cl -1, silver is Ag +1, and nitrate is NO3 with a -1 charge. So we have CaCl2. All chlorides are going to be soluble in water unless they're paired with silver, lead, or mercury, and that's not what we have here. And then we have silver nitrate. Well, nitrates are always soluble in water, so we have this. And calcium is going to go hang out with nitrate, and we're going to get CaNO3 2, and since there's a nitrate there, that will be aqueous, meaning that even though I'm writing it as calcium nitrate, they're really going to break apart. And then I'm going to get silver chloride, and that will be AgCl. All chlorides are soluble in water unless it's silver, lead, or mercury, and we actually have silver here. So that tells me that this will be a solid, and I'll go through and I will balance it. Okay, now let's go ahead and write the ionic equation. What the ionic equation means is we're going to break apart. We're going to break up aqueous compounds, only aqueous. Okay, so what that means is my calcium chloride, I'm going to write it as Ca+2 plus Cl -1, calcium and chloride ions, and those are both aqueous. And then we're going to have silver ions, and we're going to have nitrate ions. And the reason we're doing this is that if it's aqueous, it's really just ions, and so we're showing a more accurate representation of what's actually happening if you had this reaction in front of you. And those guys are aqueous. And we're going to form calcium ions, and all ions are aqueous, and then nitrate ions. And then silver chloride is solid, so I'm actually going to leave that guy there because it's solid, and so that one doesn't get broken apart. Now I need to make sure I have the correct number, and there's a lot of ways to do this. And one way is to say, okay, I had one calcium above and I have one calcium below, so that looks good. I'm looking here and here. I have two chlorides there, but only one there, so I need to add a 2. I had 2 silvers, so I need 2 there. And then I also had 2 nitrates because that coefficient carries. So that looks good. And then I had 1 calcium, so that looks good. And I have 1 calcium down there, 2 nitrates, and then 2 silver chlorides. Okay, so that's the ionic equation. And if you can get the ionic equation correct, then I think writing the net ionic equation is going to be straightforward. So the net ionic equation is just what is kind of synthesizing what actually occurs in this reaction. So we are going to cancel things and those things are typically ions that occur exactly, and that's a key thing here, that occur exactly the same on both sides of the reaction. Okay, that is how we get a net ionic equation. Both sides of the reaction. Okay, so I'm going to use my highlighter here and I'm going to say, okay, I've got calcium here. Do I have calcium ion on the other side? Exactly the same. Yes, I do. Now, if this was Ca and not Ca2+, then I would not have exactly the same. And then I have two chlorides, and I do not see two chlorides. I see two chlorines, but that's not two chlorides, so that's not exactly the same. I see two silver ions on the left, but I do not see two silver ions on the right. And then I see two nitrates and two nitrates. And so whatever's left is going to be my net ionic equation. And make sure you do carry through the states of matter. And we get this, and if we want to carry down the coefficients, we can, although they technically do reduce, so maybe it's best that we don't have them. Okay, so that's just our first example. Let's do a couple more. So in number 2, I've got solutions of potassium chromate and silver nitrate. So potassium is K+1, chromate is CrO4 with a 2- charge. Silver is Ag+1, and nitrate is NO3-1. And potassium chromate will be K2CrO4. And I know that that will be aqueous because potassium is in family 1A on the periodic table, and those guys are always going to be aqueous. And then I'm going to have AgNO3. And I know that will also be aqueous. One, the problem tells us that we have solutions, and that means aqueous. But also, nitrates are always aqueous, so I know that. And then potassium is going to go hang out with nitrate, and that's going to be super soluble, meaning that potassium is always soluble, nitrate's always soluble, so we'll have no problem getting that to dissolve in water. And then we'll get silver chromate, and chromates are always insoluble unless they're paired with group 1A, which silver is not, or ammonium, and obviously silver is not ammonium, so we'll have silver chromate, and that will be a solid. We can go ahead and get this balance. We'll put a 2 there, and then a 2. Oh, that's the eraser. We'll put a 2 there and a 2 there. And then let's go ahead and make the ionic equation. And for an ionic equation, that is just break apart anything that's aqueous. But if it's not aqueous, we don't need to worry about breaking it apart. So I have potassium chromate here, so I'll break that apart. We have K+1. Just break it apart into its ions, and then we have CrO4 with a 2- charge. And then I've got Ag+1, and that's aqueous, plus nitrate, that's aqueous. That forms K+1, that's aqueous, plus nitrate, which is aqueous. And then silver chromates, Ag2CrO4, does not need to be broken apart because it is actually a solid. And then I need to make sure I balance. So I've got 2 potassium, so I'll make sure I put a 2 there. I've got 1 chromate, that looks good. 2 silvers, so there, and then 2 nitrates as well. 2 potassiums and 2 nitrates. Now for my net ionic equation, I am going to just cross out what occurs exactly the same on each side. So I've got potassium exactly the same. Chromate is not exactly the same, so I can't cross that out. Silver is not exactly the same, so I cannot cross that out. But nitrate is, so I can cross that out. And so for my net ionic equation, that is just whatever is left over. So I have CrO4, 2- aqueous, plus Ag+1 aqueous, and that forms Ag2CrO4 solid. And then just to finish this off, I'll get this balanced, and it looks good. Let's just do one more example. This one, is a really great example, and I put some asterisks here just to indicate that it is a great example. So let's go through and do this. We've got sodium bicarbonate, that is just baking soda, but it says it's a solution. Baking soda does dissolve in water. So we've got NaHCO3, anything with sodium. Sodium's family 1A on the periodic table, so that will be aqueous, plus hydrogen acetate. C2H3O2 minus 1 is what acetate is, so we get HC2H3O2, and that will also be aqueous. Hydrogen is in family 1A on the periodic table, and this is just a double replacement reaction. Sodium goes and hangs out with acetate, so we get NaC2H3O2, aqueous, and then I'm going to get HCO3, hydrogen bicarbonate, which we can make this a little bit easier on ourselves and make this H2CO3, and so you might say that that is aqueous. But I'll tell you, this is called something, it's called carbonic acid. That is one of the acids that is in soda, such as Diet Coke or Sprite. And this guy, whenever it's formed, even for a brief second, it will break apart into H2O liquid and CO2 gas. And so a lot of people don't know what makes soda carbonated, and it's that this carbonic acid is formed. And so this CO2 that's formed is really the carbonation. Okay, so we do get a liquid and a gas in this double replacement reaction, so this does occur, and it's kind of neat that this reaction is already balanced. It just balanced itself. If only they could all do that. Okay, so now let's break it apart into its ionic equation. We're going to get Na plus 1 plus HCO3 minus 1, aqueous, plus H plus C2H3O2 with a minus 1, aqueous. And that will form Na plus 1 plus C2H3O2 minus 1. Those are both aqueous. Plus water. And then plus CO2 gas. Okay. Now, to get the net ionic equation, we're just going to cross out what occurs exactly the same on each side. So sodium will cross out, acetate will cross out, and that's actually it. So this one looks a little bit strange. We have HCO3 minus 1 plus H plus, and that forms water, H2O liquid, plus CO2 gas. And that's how that one ends.